Okay, day 2, the decay rates tab, which is really, really similar to yesterday's. We want to fill the whole space with our radioactive element, and it starts off right away. So you can see that starts to go, and you can see the radioactive element goes down, 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 and at the same exact rate, the blue stable goes up, and that's because the red atoms are turning into the blue atoms. So if we reset that and hit pause, let's see if I can do a little. Okay, so if you hit the stop button, it'll stop doing it automatically, and then you can start to do this on your own. But before we get going, if we just hit it one time, you can see that our ratio, how many atoms are we starting with, is different from yesterday's example. So we need to take a screenshot. So you have a slightly different way of taking a screenshot, right? But we take a screenshot. This is going to show our ratio and percentage in the same box here, okay? And that is going to be where this comes into play. We're going to take a screenshot of what the graph looks like for your percentages. So it's also going to show the percentage right here. And if you can, just try to make that maybe a little bit bigger. It's tough to see, but if you can do the screenshot, I'll know that. Our starting years, and then what do the atoms look like? So the atoms look mostly red, you know what I mean? Now if we start going until we get to 1 half-life, just keep hitting the step button. And remember, we're just going until we get to half of that radioactive stuff is gone. And it didn't disappear, it just changed. It decayed into stable material. So when a living organism that's made of carbon dies, the radioactive carbon stops getting replaced. We get the radioactive carbon from eating. The radioactive carbon stops being replaced with new radioactive carbon, and the decay rate can start to be tracked. So this is 1 half-life in. Okay, and you can see what the graph looks like. At 1 half-life, you have exact same ratios, 50% radioactive, 50% stable, and so we'll just take our screenshots, just like we did yesterday, of the different things. So there's my screenshot. You can see my ratio is, you know, as close as we can get to 50-50. What does the graph look like? Take a screenshot of that. Okay, so we've got a screenshot of this graph. Okay, looks kind of small, but it's fine. Years, how many years has gone by? So if this is 5,000, we're kind of noticing the same thing here. Carbon-14 always has a half-life of 5,700 years, okay? And we're estimating that from this graph right here, but you can, I mean, I'm telling you that carbon has a 5,700 year half-life. And then what does the visual of it look like? So that's the last screenshot that you're going to take for each situation. And you go like this, and you can see that it looks 50-50. I mean, half are still radioactive and half are stable. And so you're going to do that for 2 half-lives in, 3 half-lives in, 4, and then you're going to switch over to uranium-238. So carbon is really good on a short time scale. It's good for living things. The uranium is good for a longer time scale. Rocks are made of uranium. Or not made of uranium, but rocks have uranium in them. So we can use that uranium. It's going to all be the same ratios, the same graphs, the same appearance. Instead of being red, it's yellow to start. The only thing that's different is the amount of time. So instead of the 5,700 years, we're talking on the billion-year scale, just over a billion, 4.3 billion. Okay, so it just shows the main goal is you're seeing random elements that are radioactive turn stable, and just representing the percentages and trying to get a little bit of an understanding of how that works. And we're going to build off of this for tomorrow.